Okay, so definite integrals, we've been talking about this just kind of like around it, but it represents the area contained between a function and a particular axis, right? So when we're talking about something like this bounded region here, so you have your rules and all that, but if you're talking about this bounded region here, you look at it as triangular, and it's only triangular because that's a linear function. But you could find that area using the geometry formula. And that happens in a lot of cases where you have something that's a recognizable geometric situation, right? But you could also do it by finding the definite integral over that interval, right? So the benefit of using a definite integral is that you're not limited to things that are known geometric formulas, right? So you're not stuck with, well, it's not a circle, it's not a rectangular region, so I just can't find the area, you know? So with definite integrals, you find the area of anything, right? So what we do is we identify the start and the stop in terms of x, and then later on we'll do it in terms of y, but for now just in terms of x. I'll get it in there pretty good. Starts here at 0, stops there at 2. So this would become our a value, and this is our b value. All right, so we're closing that interval. All right. What we're really looking for when we're finding the area under a curve is the area between the curve and the horizontal axis. All right, but specifically, it's the area between two functions. Specifically, y equals 4 minus 2x and y equals 0. All right, so y equals 0 would be the horizontal. Y equals 4 minus 2x is the, well, that's the obvious one. All right, so you have an upper function and a lower function physically. So one is actually higher up vertically than the other one. So that's our upper function. The lower function is then subtracted from the upper function. But in this case, subtracting 0 from 4 minus 2x doesn't amount to anything. So if I did 4 minus 2x minus 0, the result would be 4 minus 2x. That's the integrand. All right, so what we would do is find the integral, the antiderivative of the integrand 4 minus 2x on the interval of 0 to 2x, 0 to 2x, 0 to 2. We'll get to cases where it's variable in a few minutes. dx. We're going to put the dx in there, but that comes from the rectangular approximation idea. All right. The idea behind all of this comes from the fact that there is a vertical distance y on this interval, actually on any interval, but specifically on this interval that's related to the function 4 minus 2x. So let me denote that here. I'll just pop it in right here. This is our vertical distance y. That vertical distance y is equal to 4 minus 2x. All right, in order to have an area, you need two dimensions. You need a height, which we have here, but you also need a base. All right, that base would be some infinitesimal horizontal distance. Now, if it were a wide horizontal distance, I'd call it delta x. But it's infinitesimal. It's supposed to be teensy tiny. So I'm going to call that dx. All right, because I want it to be infinitesimally small. All right, so if I take the product of y and dx, I would get the area of this one rectangle. If I were to integrate all possible rectangles over the interval of 0 to 2, I would get the accumulated area on that interval. So y times dx gives me a single rectangle's area. The integration from 0 to 2 gives me all possible areas added together. All right, and so that's really the origin story behind that dx that we've been just kind of taking for granted. You remember in the last unit, it was, okay, so what's the story with that dx? And I said, well, we'll get to it in the next unit. And I said that probably like 4 or 5 times. And it was like, well, really? And my answer was, aside from that, was just think of it as, like a set of parentheses. It's containing the thing that you're finding the antiderivative of. That was enough to get us through the unit, but now we have an explanation of what its true purpose is. That's indicating what the actual width is on a particular interval, right? And so the integration is collecting all of those rectangles over that interval. So that hopefully answers the long-awaited question. Here, I think, let me just reread the question. I think it was just asking us to, set up the definite integrals. You'll see a lot of questions that just ask you to set up the integrals. They don't actually ask you to do anything with them. They just want you to set them up. The reason being, well, sometimes you want to algebraically manipulate them, and sometimes that's really the final answer, because you're thinking of a multiple choice question. In a lot of cases, the big challenge is coming up with the integral itself, because the calculator can handle the actual integration part of it. Right, so I could just type this into my I could also anti-differentiate it pretty easily, but I could also just type it into the calculator very easily as well. Right, so some questions are not going to ask you to do really much of anything with it. Right, but once you get the general idea down, it's like, wait, so all we have to do is say, okay, I'm going from 0 to 2. I have this function x squared minus 0. I mean, you don't have to write the minus 0, but it's a good habit to get into in the cases where it's not bounded between the function and the axis. Dx. I'll simplify it though, just because it just feels wrong to leave it as x squared minus 0. Now the last one here, same idea, is bounded between a function and the axis. So we're looking at, on the interval of -1 to 1, 1 over x squared plus 1 minus 0 dx, or everything except for the minus 0. All right. Sometimes they want you to go the other way. And this is a pretty popular AP style question. It seems like it's kind of useless, where it's like, well, I could just type this in my calculator, or I could just do it by hand. I can integrate and do some substitution. They actually want you to sketch it out and then use the geometric formula to find it. So basically, area of a triangle, area of a circle, area of a trapezoid, anything that might make sense depending on the situation. All right, so we'll create the graph. We have a function y equals 8 minus x on the interval of 0 to 8. If I plug in a 0, I get an 8. If I plug in an 8, I get a 0. And a shaky hypotenuse. Just drawing 8s everywhere. I really don't need to do that. Definitely a triangular region. Area would be half the base times the height. So you get 32. All right. The idea behind a question like this is to really get you to demonstrate that you understand what an integral is really asking you to do, right? Because plenty of folks have made their way through calculus courses without having any idea what any of this stuff really represents, because they could just type stuff into the calculator and get answers. Ultimately, you want to get stuff right on a test, of course, but having a deep intuitive understanding of it is important also. More important, but yeah. On the day of a test, it doesn't always seem that way. All right, the important properties of integrals. I asked you to look at this. These are, at minimum, time savers. They're definitely required knowledge because, I mean, you just think of any multiple choice question on a test that involves a Roman numeral. You know, which of the following are true, sometimes true, you know, like all that crap. So, I mean, these look like they're tailor-made for that kind of question. But some of them are in the realm of common sense, I think. The first one, I think, is pretty obvious, because if you have covered no distance horizontally, then how can you accumulate any area, right? So if you're not going anywhere, how would you have any area? I mean, that wouldn't make any sense, right? So I equate things to snowstorms when it comes to integration, because when you're talking about accumulation, it just seems to make sense. So in that case, I would say, all right, the snow is falling at a rate of 3 inches every hour. After 0 hours, how much snow has accumulated? You know the answer, you know. So this one's a little weird. It makes all the sense in the world when you think about it, but it doesn't seem too intuitive at first glance. So we have the interval from B to A instead of A to B. So this one's telling us that if we swap the bounds of integration, that we would negate the integral itself, which is just, you know, how could that possibly be? So let's take a look at this in the form of a diagram. I'm going to draw an arbitrary curve, same arbitrary curve I always draw, on the interval of A to B. All right, so, but here we actually want to go from B to A. All right, so I'll draw it from A to B, but I want to go from B to A. All right, so I'll create my rectangle on that interval. That rectangle is going to have a height of y. Because I'm going in the negative direction, my delta, my change in x, is going to have a negative quantity. So it's going to be a negative delta x.
Why would it ever be negative if it's changed?
It's changed, but it's still representing a direction. So that's the idea that I'm trying to really emphasize, is that there is a direction that's in play here. But you're correct, the delta x itself would be an absolute measure. All right. So if I'm going the other way, I would have it moving in the positive direction. All right. So I'm basically taking a scalar and making it a vector. All right. So the area base times height would be negative y delta x. All right. Now, if I'm going the other way, nice poor quality rectangle for you. I'm going to try that again. We still have a y. This time my delta x is moving in the positive direction. In which case, I get an area equal to positive y times delta x. So the movement, depending on which way you're going, would have either a positive or negative result. Right? So if I'm going from right to left, I would expect a negative area. If I'm going from left to right, I would expect a positive area. Bottom line is I get a negation going from one direction to the other. So if I ever want to change the direction, so the bounds, if I want to swap them, all I would have to do is negate my integral. All right, so that's really all we're getting at with this one. All right, so if I was going from 2 down to 1, instead of 1 up to 2, I would have a negative movement. I would just negate it if I wanted to get the bounds in the positive direction. The next one, additive interval property, I think that makes sense just at first glance. You have an interval going from A to B. It's saying that if you split it at some point C along the way, that you could take the sum of those two subintervals. I think that should probably make plenty of sense. I'll do a quick sketch, but not going to spend too much time on that one. So if I take this area and add to it this area, I would get the overall area. Constant multiple rule. Same idea as derivatives, limits, sums, everything. If you have a constant multiplier, you can factor it out. Right? In terms of an actual diagram, all it's doing is increasing the height by a scale factor. Right? So if I had something like 2 times f of x, that would increase the height of all my f of x points by a scale factor of 2. So I'm doubling the heights. Right? So if you double the height of something, you're going to double its area. Right? If you double a single dimension of a figure, you're going to double its area. If you double both dimensions, that would the square the scale factor and then multiply by the area. But that's a different story. But here we're only just impacting one single dimension, so it wouldn't have any more impact than just being constant multipliers. Sum rules, the same idea as derivatives, so I think that's pretty solid, I think. Preservation of sign. If f is integrable and non-negative on a to b, then you would expect your area to be non-negative, right? So it would be greater than or equal to 0. So that's basically telling us that if you have a curve that's above the x-axis, you should expect a positive area. Right? If it's on the x-axis, it has no height, so you would expect it to have no area. If it's below the x-axis, then you would expect it to have a negative area. All right? So it's allowing for areas to be negative. Preservation of inequality, that should make sense, just at first glance. Because if one function is physically higher than another, then it would contain more area. Right? So again, since these antiderivatives, these integrals, are representing the accumulated area over an interval, then if the height of the function would impact the amount of area that's accumulated. Right? So I think that should make plenty of sense. So we'll put some of these in action right away. Like the first one, right off the bat, we know that this one's equal to what? 0. Now, in this one, we have a constant multiple. All right, so I could pull that out. So this would be 15 times the integral from 2 to 4 of 1 dx, but I'm just going to write dx so that it coincides with the information that was given. So 15 times 2, which would be 30. Now, just as a quick side note, whenever you're taking the antiderivative of a constant, it's very easy to do without actually doing any real, well, seemingly any calculus. So let me just kind of pull this one off on the side here. Because again, we never want to lose sight of what we're looking at. This is saying that we have a function y equals 15. All right. Y equals 15 over the interval of 2 to 4. So I could just create you don't even have to do this on paper, you just do it in your head. But y equals 15 over the interval of 2 to 4. And it's not drawn to scale, obviously. But what it's asking us to do is find the area of that figure. All right, so we know that the base has a width of 2, and it's rectangular. Base has a width of 2, the height is 15, 2 by 15 is 30. All right, so there's really no need. I mean, it was nice that they gave this to us, but we didn't need it. We could have figured it out. Also, you don't even need to draw the diagram, because once you really realize that it's whatever the height of your function multiplied by the length of the base, then all you really need to do is find the difference between the bounds. So anytime you're finding the antiderivative, the integral, definite integral involving a constant function, all you got to do is find the difference between the bounds of integration and multiply it by the function itself, and then you have it. Right? So that would work in any case, right? As long as it's a constant function, right? So no variables. Right? So difference between the bounds would be 2 multiplied by the 15, you get the 30. Right? It saves you a lot of time. And that's kind of the name of the game at this point. Right? In the next one, we have a sum rule at work, so I can break it apart. So the first part of this is a rule that they gave us. They just did the work. We could have figured it out if we wanted to. Incapable of drawing a line. 60. Based on what I just told you.
But it says x cubed dx is 60.
Oh, I just wrote squared for some reason. I have no idea why. Oh, no, I'm not little. I'm totally locked out. Oh, you know what I think it is? I think when I adjust the size, that locks me out of erasing. I'm going to have to put that to the test later. What's this bad boy going to be? 8. 8. Yeah, because difference between the bounds multiplied by the integrand. Okay. So we have 68. All right. All of these could have been done on a calculator, but I think, I mean, at least for definitely the first two, it takes longer for you to type them into the calculator than it does for you to figure it out in your head. All right, so just something to keep in mind. I'm going to, the remaining time that we have, tackle these trig problems with you. They give you a nice rule here, being given that from 0 to pi, the sine function contains an area of 2. And using what you know about integrals, graphing curves and using a little bit of intuition, maybe a lot, determine the values of the following integrals. All right, so just quickly draw a nice little sine function here. I'll do it over 0 to 2 pi, just to get the full wave. They're telling us from 0 to pi, which would be the halfway point, that contains an area of 2. All right, I'm going to split it up even further. Put a pi over 2 here, a 3 pi over 2 here, and I'll get the 2 pi here. All right. If I know that I have an area of 2 on this whole interval from 0 to pi, what do I know about this subinterval? What's its area going to be?
Half.
Half of that, which would be 1. All right. So I know it's going to be 1 unit. Intuition. All right. The idea being that we know that there's symmetry in a sine function. All right. Now it looks like we have some point symmetry here through pi comma 0. What's this subinterval's value going to be? From pi to 3 pi over 2. Well, it's below the x-axis. -1. All right, so we have all that information, which means that if I needed to, for example, figure out, bless you, the area from 0 to 2 pi, bless you, it would be an area of 0, all right? Because I have equal parts positive area and negative area, so they cancel out, all right? If I needed to find 0 to 3 pi over 2, I can do a quick sum and get it. It would be just a positive 1, all right? But that sets me up for a lot of the problems that follow. Right, it asks me for pi to 2 pi, -2. 0 to 2 pi we already really addressed. Just by drawing the diagram. 0 to pi over 2, already accounted for. For D, it's a little different, but nothing too crazy. It's just what I want to do here is use one of my properties first, and that's the sum property, 0 to pi of 2 dx plus 0 to pi of sine x dx. All right, so what is the definite integral on the interval of 0 to pi of 2 dx? 2 pi. And then the other one?
2.
Just a 2. Either from the diagram or from the given, either way. All right, for E, we have a little constant multiple action going on there. So I could pull out the 2. So 2 multiplied by, same deal, right? 2 multiplied by 2. And we'll get a 4. It's a little funkier after that. Part F doesn't seem anywhere related to the given function, but it's very related. I'm going to draw a quick sketch of that, and you'll see. It's kind of off on the side here. By the way, quick question. What does that x minus 2 tell us? Move it to the right. Yeah, it's a horizontal shift. Right? In this case, of 2 units. Right? The coefficient of x is 1, so it's definitely a 2-unit shift to the right. Right? So instead of starting off at x equals 0, it's going to shift to 2. And then instead of having a max, I'll just draw the full original sine wave. I'll extend this. Instead of having a max at pi over 2, it's pi over 2 plus 2, and then pi plus 2 for the midline, and so on. So it's going to look something like this. All right, so what I get from this is that it's the same sine function, just shifted over. I'm looking for the area between 2 and this location, which would be pi plus 2. Sorry, 2, that's not pi plus 2. That's 2 pi plus 2. This one will be pi plus 2. So I need this area, which would be what? 2. Now, once you realize it's the same figure as what we started with, then you can work off of that. Although that's a much nicer drawing than the original one. The dotted black, I mean, that is just beautiful. I mean, that's a gorgeous diagram. Anyway. I don't even know how that happened. Now this one seems to be a change in variables. But it's actually the easiest problem on the whole page. It's just zero. Right? So just a quick sketch. I'll just do it like this. Oh boy. I had to make up for the good drawing. So what it's telling us is that we have, and now u, I mean in this case it could be replaced by x's. It really would make a difference because we're dealing with the bounds going from negative pi to pi, but these bounds are in terms of u, right? So it's really the same function. Maybe it has some composite aspect to it, but it's going from constant bounds, so it leads me to think that that's probably not the case. All right, so negative pi, positive pi, 2 areas that would offset each other. All right, so equal parts positive and negative. All right, but even if it were, some other inner function, you have that point symmetry through the origin. All right, because the sine function is an odd function, if the bounds are opposite of one another, they're always going to cancel out in terms of area. All right, so that always is going to happen with odd functions. If you had an even function, that's a different story. You would actually just double it. It would be, if you were going from negative pi to pi, but for, let's say, a cosine function, whatever the 2 parts are on either side of the y-axis, those would be equal to one another. All right. Now, for h, what do we have here? What does that x over 2 tell us? It's a constant multiple of x, but how does that impact the graph? It affects the period. Okay, so the period is 1/2. I'm sorry, the frequency is 1/2. The period 4 pi. All right, so it's double the width. All right, so what that's telling me, oop, that's the highlighter, is that I'm going to get the same height, because the amplitude is still 1, of the sine function, but it's going to be double the width. Right? So where I would have to go out to 2 pi normally to create one full sine wave, I'd have to go out to 2 pi to only get half of a sine wave. All right? Or 4 pi to get the full thing. But if I look at it this way, poor quality. Not much better. All right, so I've doubled a single dimension. So what's going to happen to my area? Double. All right, so instead of 1 and 1, it's going to be 2 and 2. All right, so this would be 4. Last one's cosine wave from 0 to pi. Let me do the full shebang, poor quality. But as you know, a cosine wave is just a shifted sine wave. All right? So if I break this up into parts like I did for the sine wave, each of these areas would have the same quantity. So from 0 to pi, I'd have a total of what? 0. All right. So I'm going to put a star on examples 5 and 6. So the problems that I started on the previous page and also these, do those for homework, and we'll go over those tomorrow.